guys, this video is going to look at Walding Chapter 22 in-text questions. We're going to start with 11. Looking at number 12, it does look to be a fairly long question in terms of the math, so we might get through to 13, maybe through to 16, which is the next set of in-text questions, as they look to be a little bit shorter than this one. The longness is going to come from redrawing these resistor diagrams. So we'll see. Check the title to see more questions we cover. So question 11 reads, a student sets up an electric circuit with two 25 ohm resistors in parallel connected to a battery of EMF 12 volts. She wishes to calculate the total circuit current and the individual currents through each resistor. Draw a circuit diagram for what she would use and calculate the value. So let's start off by drawing the diagram. We're told that there are two resistors and they are in parallel. Okay, so that means that they are next to each other. We're told that there is a battery with EMF of 12 volts, and that is it. Now, we're asked to find, so there's our circuit diagram, nice and straightforward. More complicated ones, like if you're looking in the textbook, the question to the side, number 12, the diagram to the side, that'd be really hard to describe and you to get it right. So really, descriptions are going to be simple things like 3 resistors in parallel, or 2 to 5 resistors in series. You might sometimes have 1 resistor in series with 2 resistors in parallel. That'd be about the most complicated type of language you can get. Realistically, you're probably not going to see anything more complicated than this, though, on a worded question. Anything more is going to have a diagram. Now, the question is asking us to work out the current, so total circuit current and the individual currents. So we want to know what is the total current running through the whole thing, and what is the current being run through each of these resistors. We're told that R1 will equal 25 ohms and R2 here will equal 25 ohms as well. Now we could draw some resistors on this. Sorry, not resistors, sorry, with some ammeters on this to help us visualize what's going on. So if I get rid of that line, I could draw an ammeter here. Now that ammeter would read how many electrons are leaving the battery and passing through here before getting off to this. So that would give us the current for the entire circuit. Meanwhile, I'll redraw some of these lines over here. I could put an ammeter there. I could put an ammeter there, so that I could work out, well, how much current is flowing through this resistor through this point here and then back into the current. Now let's draw the path of the current. Remember, current always leaves the positive terminal. It's going to go around here, and then it's going to hit a junction, and that means it's going to flow in both directions out of the junction. It's going to go through this, back together before rejoining. So remember Kirchoff's law that the current in must equal the current out. So we know then that, say at this point here, the current total must equal the current that is going into resistor 1, so we'll call that I1, and into the current of resistor 2, we'll call that I2. Okay, let's work out firstly the current going through the total circuit. Remember, we need to use an equivalent resistance here. So we have 2 circuits in parallel, so we need to use our parallel law. So for our parallel law, 1 over resistance total equals 1 over resistance 1 plus 1 over resistance 2. 1 over resistance total is going to equal 1 over 25 plus 1 over 25, which equals 2 over 25. And so invert that, because this is 1 over RT, so this would become RT is equal to 25 over 2. Now we could work that out. If we go and stick it into a calculator, we'll get some number out of that. I prefer to leave it as a fraction, unless it comes out as being a whole decimal. My calculator is not here, so let's load up the computer version. Calculator, and if I do that, 25 divided by 2 we get it's 12.5. So that's at least a nice simple decimal that we could work with. It's not going to give us any rounding errors down the track. Leave it as either. I'm fine with fractions. We know the total voltage. We've been told the battery has 12 volts, and therefore we know that we can work out the current, because remember we have Ohm's law that I total will equal V total divided by R total. Okay, or I equals V over R. We've got V, it's 12. We've just worked out resistance, it's 12.5. And if we stick those together, let's see, where's my clear button on this thing? There it is. 12 divided by 12.5 gives us an answer of 0.96 amps for the entire current. Now, let's have a look at this diagram again. We know now that there is 0.96 amps coming up to this point. And then it gets to here, it splits into two. So the two numbers, however much is flowing out, must equal 0.96. And being as they've both got the same resistance, then it's intuitive, because they're the same resistance, it should be the same number. Okay, and if we would half 0.96, we'd get 0.48. Now, that's not a calculation, that's not a proof. We can sort of use it to help guide us, but we need to actually show that it is. And the way we're going to do that is using another law that we've learned the other day, is Kirchoff's loop law. Now, Kirchoff's loop law, remember, says that for an entire path around a circuit, the sum of voltages must equal to 0. So let's draw the path. We go, I'll do this in red. So let's draw one path. We leave here, we go here, we can choose to go one way. Let's go down, we go through here, back up, and then down and back to here. So we can see if we go around this path, it gains some voltage here, and it only goes through one resistor, so it has to lose all its voltage there. Okay, that's a sort of hard thing to wrap our head around, that it must lose all its voltage there. The other way of doing this is because this is equivalent to the circuit that, let's redraw this battery into one resistor with 12.5 ohms. Again, we could work out, well, we've got the current, so that means the total resistance here is just going to be, well, 12, because we're going to end up reversing this equation. Okay. So I hope you can see why that has to be 12 volts across there. So let's remember our basic definition, our basic understanding of Kirchoff's law is that whatever is given to it must get used up. It's only got one stop, so all that voltage has to be used there. So let's look at the circuit we have there, or the circuit component. We have that resistance equals 25 ohms. We know that the current flowing into it is unknown, because that's what we're trying to work out, and that the voltage getting used is equal to 12. Again, we need a current. This was resistor 2. So let's work that out. The current in 2 equals the voltage in 2 divided by the resistance used in 2. Ohm's law, as I've said in class, applies to every single component on that circuit. Equals 12 divided by 0.96, that's the current. 25 ohms. I was looking at the wrong resistance. We want that resistance. 12 divided by 25. Go over to our calculator. 12 divided by 25. Okay, while that would be a fraction, we could leave it as, because there's no common denominator between, no common factor between 12 and 25. We do get the answer 0.48, which is what I predicted at the start, 0.48 amps. Now, we don't have to work out resistor 1, it's got the same resistance. Resistor 1 and resistor 2 have the same thing, so therefore the current is going to be the same as we intuited earlier at the start. Therefore, I1 equals 0.48 amps. Okay, and that's all the working you need to show for a question like this. And you don't have to worry about proving I1. We can see that, oh yeah, resistance is the same, voltage is the same, therefore current must be the same as well. Let's move on to question 12. We have a picture. Consider the electric circuit shown in figure 21.1. So there's an ugly looking thing to the left. Calculate the current flowing through each resistor and the voltage drop across each resistor using the laws of circuit analysis. So those are our Ohm's law, our Kirchoff's laws, and our resistor laws. Fully describe your steps and redraw the appropriate equivalent circuits at each step. Okay, now I'm not going to do the describing steps. We can use annotation though. So for example, let's first off draw the circuit. We have a 15 volt battery. I'm not going to draw both battery cells, it's a bit redundant. We have one resistor with 5 ohms going into two 10 ohm resistors. Now you'll notice at this point, so far my picture is the same, but what I'm about to do for the second one will make it a little bit different. I don't like what they've done there. I much prefer to do it like this, because it emphasizes, that's a weird looking ohmic symbol, it really emphasizes that these two are just in parallel with each other. Alright, so we've got something like this. We need to work out our total resistance for the circuit. And the good thing is these are both 2 sets of 10 ohms. So whatever this one is equivalent to, this one will be the same. So step one will be equivalent resistance using 1 over RT equals 1 over R1 plus 1 over R2. Okay, so let's work that out. 1 over RT is going to equal 1 over 10 plus 1 over 10, which equals 2 over 10. And that means RT equals 10 over 2 equals 5 ohms. So both of those are going to be 5 ohms. Let's redraw this. So that would become battery 5 ohms, 5 ohms, 5 ohms, back home. Step 2, now we need to deal with these three. Good thing is they're all in series now, so equivalent resistance of 15 volts of series. And if we draw that, well, we're going to have RT equals R1 plus R2 plus R3. When they're in series, remember, we just add them together, equals 5 plus 5 plus 5 equals 15. Can't draw omegas for save myself tonight. 15 ohms. So therefore, let's redraw the equivalence again. Battery, resistor, back home, 15 volts, 15 ohms. That's something I really hate doing, I'll be honest with you. I don't really enjoy doing all these circuit after circuit after circuit after circuit. It does get a bit tedious in my opinion. Alright, we can work out the current here. So we now have the resistance total equals 15 ohms. We have the voltage total equals 15 volts, and we can work out the current. Remember that current equals V over R equals 15 over 15 equals 1 amp. So that means there is 1 amp of current running through the whole thing. Now, in the diagram, they identify that this resistor, this very first resistor up here, is called R5. We've got 3 and 4 here and 1 and 2 here. We'll get to those ones a bit later. So that means that if I was to slug, I'm going to redraw my picture but a bit bigger, so we've got something we can keep going back. Let's draw that again a bit better. That we can keep going back and referring to. 15 volts, 5 ohms, 10 ohms, 10 ohms, 10 ohms, 10 ohms. Alright, we know the total current, we work that out here, 1 amp. So if I was to take this circuit and put an ammeter here, that would read 1 amp, because that's the amount of current that is leaving the battery going into this first resistor. If I was to put an ammeter here, it would also read 1 amp, because whatever leaves here has to go through here, get to here. But if I was to put a ammeter here, remember it's come this way and then it's split. Some of the current's going to go here, some of the current's going to go here. It's going to come back together, and so over here, if I was to put a ammeter, it would read 1 amp. If I put one over here, it would read 1 amp. It's just that in that section where it's split, same here and same here, it's not. Okay, so this one's not going to be 1 amp, it's not going to be 1 amp here, 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 but it will on these other places. Okay, because at this point all the current needs to move together. Okay, so if you're uncertain of that, rewind it, listen to what I've just said again. So in these sections, because there is the total current we worked out as being 1 amp from those original things, we worked out the equivalent resistance, so that we had just one resistance number to use for the entire circuit. We used that with the voltage to work out the current, I equals V divided by R. And that told us the entire circuit has 1 ampere of current going through it. And since that means 1 ampere left the battery, it hasn't split yet, all of that section, because it hasn't split, must be equal to 1 ampere. When it gets to here, then it splits, no longer 1 ampere. Comes back together, 1 ampere. Splits, no longer 1 ampere. Comes back together, 1 ampere. Remember, current must add on both sides. Whatever goes in equals whatever comes out. That's our junction law. Now, I'm going to deal with this resistor first, resistor 5, because we've got both numbers we need. For the current going through 5 is equal to 1 amp. It'll be 1 ampere, it'll be 1 ampere. The resistance going through 5 is 5 ohms. We've been told that. So the voltage on 5, remember, equals IR, equals 1 times 5, equals 5 volts. So we're told that it has to lose 5 volts going through here, which means that the other 10 volts has to get used up across here. Now I'll swap over to my red colour. Let's draw up a path. Come out here, loses some voltage. Come to here. Let's go down first. Here. Now let's go up. Okay. So here it loses 5 volts. Here. Oops. Here it loses some voltage, we just don't know how much, and here it loses some voltage. Sorry, I did it at the top there, didn't I? Here it will lose some voltage. Again, we just don't know how much. So we need to look at these things. What we do know, though, is that whatever voltage it uses here will be the same as the voltage it uses here. They have the same resistors, and they have, because they, what's the word I'm looking for? Because they're parallel, they're going to have the same voltage being applied to it. Voltages in parallel are always the same. Okay? Currents in parallel are not always the same. They might be different depending on what the resistance is, but the voltage will be the same. Okay? The current is heading out, it's getting pushed at these two things with the same amount of push. The amount that goes through might end up being different, but the push is the same. Okay? it's kind of like having two doors. One door might be a lot bigger than the other. The push against each door or each doorway would be the same, but because one has a much lower resistance, we get more flow through. The other one is a lot smaller, so we get less flow through because the resistance is higher. Okay, so we could use a big simultaneous equation to work this out, but I'm going to go back to here, my 5 ohm resistor, this equivalent circuit we did here, to work out how much is actually going to be lost across it. That being said, being as we can see, well, here we'd have 1 ampere, 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 and we've got 5 ohm resistors on each of them. We can see it's going to be exactly the same thing we did there. It's got a resistance of 5, it's got a current of 1. So the voltage drop across each of these, or each of these equivalent resistances, must equal to 5. So let's go back to my black pen. So I believe this one is called R3 and R4. So the voltage for 4 is going to equal 1 times 5 equals 5 volts. Okay, it's going to be the same for all the rest of them. So it's going to equal voltage 3 equals voltage 2 equals voltage 1. They all have a 5 volt drop. Let's work out the current. Now, being as they're both 10 ohm resistors, we'd infer they should be the same. Let's see if we're actually true for that. We know the voltage. We know that V equals 5. We know that current is unknown. We know the resistance equals 10. And if we put that together, we get that I equals 5 divided by 10 equals 0.5 amperes. Okay. Now, the way you can set up a big simultaneous equation for this is that we write the voltage pathway for going around the whole thing. That the voltage from the battery plus the voltage from resistor 5 plus, say, the voltage from resistor 3 plus the voltage from resistor, let's say, 1 must equal to 0. And then we use our Ohm's law to work that out. We know that that is 15, and this one we worked out as 5 because that one was quite simple. So that should be minus 5 because it's getting used up. Voltage 3, in this case, we don't know what it is, but we do know it must equal IR. Okay? And for voltage 1, same thing. We don't know what it equals, but we do know it must equal IR. That equals to 0. The resistances, again, we can work out as being tens. Okay? So that's going to give us 10 E plus 10I plus 10I. These are different I's, so I3, I1 equals 0. We can see, there's a whole bunch of 10s here, so let's divide everything by 10. So 1 plus I3 plus I1 equals 0. At this point now we need to work out, well, we have 2 unknowns here, we can't use that. We're going to have to work out another set of equations to figure what that out's going to be. And remember, we have our sorry, what's the word I'm looking for? We have our junction laws that we can use in this case to write an equation about I's, that the I3 and I4 would be equal to whatever the original input is, so is equal to 1 ampere, and that, what's the other word I'm looking for? I2 and I1 would also be equal to it. We would have to then do up another circuit involving, say, voltage 4 and voltage 2 to get rid of those extra variables we just counted. It's a really long, tedious process. I don't like doing it, and I'll be honest, you're probably not going to have to worry about any of those in this unit. So, all of that, unless you're really keen on electronics, don't even worry about it, okay? Just focus on what we've done here, and we'll see what we need to do when we get to some more difficult questions in the review stuff, okay? Focus on what we did there in terms of that intuition and using our equivalent circuits to work out the voltage. Remember that voltages in parallel are always the same, okay? Which would let us say that V4 equals V3, and so there's some more equations that we could use. As I said, very, very annoying. Okay, we're making pretty decent time. Let's move on to question 13. Now, question 13, I didn't really do much stuff on power in class because power is just a definition. It's generally better to sort of have a play with these things and see how it goes, because they've got to be very simple formulas for these first few questions. Question 13 reads, calculate the power rating of a light bulb operating at 240 volts and 0.6 amperes. So let's write down the numbers we have. We have 240 volts and we have 0.6 amperes. So 240 volts, that's a voltage, obviously. So V, and we give it the symbol V. 0.6 amperes, that's a current, we give it the symbol I. And we're asked to calculate the power rating. We just want the power. Power equals don't know. Now, we have a formula for power in currents, and that is power equals current multiplied by voltage. Let's substitute those in. It equals 240 multiplied by 0.6. And that should give us 240... Oops, clear. 240 multiplied by 0.6 equals 144 watts. Now remember, it's spelled with a double T, not an H. Okay, let's go check our answer. Yep, 144 watts. Now remember, the symbol for watts is just W. On to 14. What is the resistance at normal operating conditions of the following appliances run from the 240 volt AC mains? So first off, we've been told that there is a 240 volt mains, and it's going to be our voltage, our power supply. We've got a 50 watt television set. Okay, so for A, we have that power equals 50 watts. Do we have a formula? And we're asked to work out the resistance. Resistance equals dunno. Do we have a formula that links these three things? Yes, we do. Okay, and if I scroll back up to it to double check it, yes, it is V squared over R. So P equals V squared divided by R. And that would equal then 240 squared divided by 50. Let's chuck that in. Sorry, no. I just had a complete stupid moment. So 50 would equal 240 squared divided by R. Yes, what I had written was correct, but it didn't equal P. So R equals 240 squared over 50. 240 squared divided by 50 gives us a resistance of 1,152 ohms. Let's double check that. And 14A, yep, correct. A 1 kilowatt hairdryer. Again, we've still got the same voltage. This time we've got power equals 1 kilowatt, so 1,000 watts. Again, we want to work out resistance. We don't know what that is. So P equals V squared over R. R equals V squared over P equals 240 squared divided by 1,000. Take that previous number, 50, because it's still going to be the same, divided by 1,000 equals, so resistance equals 57.6 ohms. Okay, so we can see here then, if we have something that is drawing a certain amount of power and you've got the same amount of voltage being applied to it, then you need to have a smaller resistance to allow that power to run into it. And they've rounded off to two significant figures, but I'd leave it as this. C. A 100 watt light bulb. Power equals 100 watts. That's a fairly bright light bulb. Resistance equals I don't know. We've seen this a couple of times. Resistance equals V squared over P equals 240 squared over 100. Okay. Divided by 100 gives us a resistance of 576 ohms. Alright, so those ones should have been reasonably straightforward. Remember that there are a lot of power formulas because we can use the power formula P equals IV along with Ohm's law in every combination in order to attain a whole bunch of other formulas. They'll all be given to you in your exam, but just be aware. A heater is connected to the normal main supply. If the resistance element has a value of 8 ohms, how much electrical energy is supplied to the heater in 5 minutes? So we've said a normal main supply. Okay, now what is the normal main supply? The good news is question 14's kind of got that there. The normal main supply means that voltage for Australia equals 240 volts. Okay? That's why I said if you switch your computer, the slide switch at the back of your computer, it will just not work because it's expecting 240 volts. It'll blow up because it's expecting 180 volts. Instead, you give it 240 volts. Boom, bye-bye computer. In America, it's the opposite. If you switch it across, it's expecting 240, only gets 180, and just doesn't turn on. So for us, it blows up. For them, nothing happens. So I wouldn't expect you to remember that. That would be something that would be given to you on an exam as a constant, for example. We have a resistance. Resistance equals 8 ohms. And we're asked for how much energy in 5 minutes. We have a T equals 5 minutes equals 300 seconds. And we want to know what energy is. And that time tells me we need a power, because power multiplied by time is going to give me energy. You'll commonly see it written as work, but remember work is energy. Okay. So same formula as before. P equals V squared over R. So P is going to equal 240 squared divided by 8, which will equal 7,200 watts. Remember, a watt is defined as 1 joule per second, okay? Or that power equals energy divided by time. We've got time, we need energy, so energy equals power multiplied by time. So it's going to equal 7,200 multiplied by 300. Gives us an answer of 2.16 million, so 2.16 times 10 to the 6 joules of energy is provided over 5 minutes. And we'll go and double check that. 2.2, so they've rounded, but that's okay. Let's look at 16. It requires 4.2 kilojoules of energy to raise the temperature of 1 kilogram of water by 1 degree Celsius. So those of us who did thermo last year, that should be a number that's fairly familiar to you. Remember, that's a heat capacity of water. If an electric hot water system is rated at 6.5 kilowatts for 240 volt AC, and it holds 250 kilograms of water, well, calculate its coil resistance, the energy required to heat the water from 15 degrees to 80 degrees. Okay, this is a longish question, or a lot of pieces of this question. So let's start off with identifying what we actually need to find. So for part A, we're asked for the coil resistance. So we're looking for an R. R equals I don't know. Let's go through what we've been provided here. We know the heat capacity of water. We give it the symbol C, but we're not going to worry about that too much. That's not going to help to start off with. We've been given a 6.5 kilowatts. That's a power rating. Remember to look for the unit. So we have 6.5 kilowatts, and that's a power. Okay, that unit watt clues us in, or equals 6,500 watts. Okay, the next number we see there is a 240 volt AC current, so that means that voltage equals 240 volts. we already know we can use these to solve for resistance. So remember, we found that resistance equals V squared over P from those previous equations. Let's type that in, 240 squared, and then we're going to divide it by 6500. Sorry, I should put that in clearly for us. 240 squared divided by 6500, and that equals that the resistance should be 8.8 ohms. Okay, so fairly small number, it's a very low resistance. Now, what we know here is that it takes 4.2 kilojoules of energy. We know it gives this much energy per second. Okay, so power equals energy over time. We saw a question like this in class. I said, well, what time should we assume? And let's use the easiest time. Let's use 1 second. So let t equal 1 second. Therefore, energy equals 6,500 joules. We're after kilowatt hours. We'll get to that in a second. I'm going to get rid of that for the moment. I didn't notice the unit they want us to use for energy. Okay, we'll talk about kilowatt hours in a minute. So let's work out the energy. It takes 4.2 kilojoules, let's write that, kilojoules per kilogram per 1 degree Celsius. So let's look at these. How many kilograms do we have? The question says we have 250 kilograms. Okay, so if it takes 4.2 kilojoules for 1 kilogram, what are we going to do to work out how much for 250 kilograms? We're going to need to multiply. And this is per 1 degree Celsius. But we're not going up 1 degree Celsius. We're going 15 up to 80 degrees Celsius. Well, how much is that? That means the delta T, the change in temperature, is going to equal 65 degrees Celsius. So per kilogram, we've got 250 kilograms. Per 1 degree Celsius, we've got 65 degrees Celsius. So let's use that. That gives us then 4,200 joules multiplied by 250 kilograms multiplied by 65 degrees Celsius. Okay. And that gives us a total number of 4,200 multiplied by 250 multiplied by 65 equals 6.83 times 10 to the 1, 2, 3, 4, 6, 7 joules required. Now we're after power. Okay, we've been told that this is a 6.5 kilowatt system, so it's providing 6.5 kilowatts per second. Okay. What we want to know is, well, how many hours would this actually take then? Because we're after how many kilowatt hours. Okay. We know then that we have this much being needed, so let's work out how many seconds it would actually take. So the amount of seconds is going to equal 6.83 times 10 to the 7 divided by that 6,500, and that will give us, divided by 6,500, note I haven't rounded on my calculator, 10,500 seconds. Okay, that's a pretty large number. Let's divide by 60, gives 175 minutes. That's a bit clearer to see. Divided by 60 again equals 2.92 hours. Okay, so we know how long it's going to take. We now need to work at this idea of kilowatt hours. Okay, so how do we convert the amount of energy we need and the amount of time that is into that? Now I'm going to scroll up and look for an actual stated definition. I don't think there's actually one in our textbook, which is a little bit annoying. Let me have a look in our index just so I can give you a reference for this. Index. Okay, see, if you have a unit that you're not 100% sure on how to convert to, look it up. Okay, it should be in the back. Kilowatt hours on page 488. Okay, what? Okay. So kilowatt hour is the amount of energy used by a device rated at 1 kilowatt over a period of 1 hour. That doesn't really quite answer our question, does it? Let's see. Let's look for some conversion. So I'm going to go to Google, and I'm going to just type in the phrase. Let's get my keyboard in here. Just hit my mouse a bit. Let's see. Convert to kilowatt hours. Let's see what we find. Now, and the reason I'm asking this is because sometimes it honestly just drives you up the wall. We know how many joules. Okay. I didn't need the time from the look of it. I have a stated value here that 3.6 times 10 to the 6 joules equals 1 kilowatt hour. Okay. Okay, so let's take this number, 6.83 times 10 to the 7, and divide by 3.6 times 10 to the 6. So, times 16, because we know that, so I'm just converting back up to my number here. Okay, I've got my number here. 6.83 times 10 to the 7. Yes. Okay, so we know it's this many joules. We're told that this many joules equals 1 kilowatt. So dividing these two numbers will tell us how many kilowatts there actually is. 6.83 times 10 to the 7 divided by 3.6 times 10 to the 6. And it gives us divided by 6, 1, 2, 3, 4, 6. Wonderful. Cute. That's weird. That shouldn't give me an answer. That's small. I'm going to need to do that again. Let's clear that. 6.83 exponential of 7 divided by 3.6 exponential 6 equals. Why is it giving me such a small number? That shouldn't be anywhere near like that. Let's use Wolfram Alpha. Obviously, my Windows calculator is not doing too well. 6.83 times 10 to the power of 7 divided by 3.6 times 10 to the power of 6, because that should be closer to around 18-ish. There we go, 18.97. So that equals 18.97 kilowatt hours. Let's go and check our answer key. We see that for chapter 22, question 16b, energy is 18.9 kilowatt hours. So with a bit of rounding error there, we would have 19 rounded off to one decimal place there. So that's pretty close, which is what we want. Remember, rounding errors don't get you marked down. Okay, you just need to show working. Now, let's look for a actual good explanation on what a kilowatt hour is. So it says that a kilowatt hour is the amount of energy used by a device rated at 1 kilowatt over a period of 1 hour. So let's think about this for a second. We have here that this device, so we're going to try to work out how we got to this number. We have this device, or yeah, it's how we got to this number. We have this device at 6,500 watts, so it's joules per second. We would need to divide this number by 6.5 to get it down to a kilowatt. Okay, so that means it would use 1 kilowatt of time of energy in a fraction of a second. Let's try to work out how large that actually would be. So if we let energy equal 1,000, then we would have, and that's our power, we can work out time. So that would give us that 6,500 equals 1,000 divided by t. So t equals 1,000 over 6,500. So that equals 10 over 65. 10 divided by 65 gives us a time of 0.154 seconds. Okay, but we've got to do this over an hour. So I would wonder if this is, say, the amount of that into an hour. So an hour, remember, is 3,600 seconds. If we divide that by 0.154, we get 23,376 units of seconds here. I don't think I can use that number to work it out. Let's see if we can find a good article. Joules, kilowatt explained. Let's have a look. Okay, so I found a website called Energy Lens. Okay. Blah blah blah, blah 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 blah. What is the difference? Kilowatt hour is a measure of energy, kilowatts is a measure of power. Okay, so we were on the right track with our discussion of energy, so our value of joules. Okay, yeah, calories and the BTU. Okay, I'll keep reading through this. Okay. Trying to find a conversion on this website to help us understand the relation. Here we go. So, energy equals power multiplied by time. Yep, we know that. That's from our original formula. They've then told us then that kilowatt hours. Okay, this makes a bit more sense. So let's use this formula. E equals P times T. Okay, this is just a rearrangement of P equals E over T. This stuff here doesn't seem to be useful, so let's just write that out for now. Therefore, kilowatt hours equals kilowatts multiplied by hours. Okay, that seems to make sense, okay. If we keep going through this. We have our power. We knew that was equal to 6.5 kilowatts. We don't know our hours. Let's work backwards. Always good with something like this. If you don't understand something, work backwards. Now, they used 18.9 in the textbook. We don't know what T they actually use, so let's try to figure that out. Okay? We've just used it. Oh, well, I've just used a conversion tool and just gone, oh yeah, let's figure that out. So let's see what this actual thing would be. So we have that would be T, therefore equals 18.9 over 6.5. That's going to be a little bit under 3 hours. So 18.9, well, oops, my computer's being weird. 18.9 6.5. I hate using Windows calculators. Oh, that gives me that 2.907 hours. Didn't we work that out before? There we go. That's really close to that. Oh, alright. So, before what I've used over here is I've used the amount of energy that it takes to heat up this thing, and I've divided it by the kilowatt hours, and by the kilowatts, and by using that I've then worked out the amount of time, 2.92. Now that had a slight rounding error in it, and by doing this manually using the answer in the back of the textbook, I now have got a time of 2.91 hours. So that equals 2.91 hours. So that means then, if I take that and put it into here, I would get close to 18.9, which is what the answer at the back of the book says. So, looks like then to work out kilowatt hours, what you need to do is take the kilowatts, pardon me, work out how many hours it would actually take to gain the energy you're interested in, and we've done that just using that energy formula from the information we were provided about the water and how much mass there was and how hot we want to make it. So that gave us the total energy. We can use these two things to work out the time it would take, and then if we multiply these two together, we end up getting the value in kilowatt hours. So there should be a conversion factor, and I imagine then looking at these numbers, we should be able to arrive at that conversion factor. So this could be a number that you could remember. It may be something that would be defined, but being as I've just kind of worked out here that kilowatt hours is a unit of energy, it's just equal to power times time. When power is in kilowatts and time is in hours, you might be able to work it out. Okay, it could be worthwhile just remembering that fact, just something to commit to memory for that one exam. However, might be something that is worthwhile understanding a bit in order to figure it out. Now, the article I've got it from, I will include that in a link in the video, and if you scroll down to around the 2/3, 3/4 mark through it, you can kind of get to the bits where they start talking about a formula. Oh, we've got some mentions here, so they've just multiplied it by the amount of time in hours. Okay, cool. Alright, so that's not too bad. I think that sort of makes sense. It's a bit of a weird idea. Honestly, we don't work with this unit very often, so you're probably going to forget it after this exam anyway. Don't super stress about it. Just know that kilowatt hours is a unit of energy, not of power. Alright, I'll leave you with that video, and I will see you for the next one when we will look at, let's see what comes up next. Question 17, I believe, will be a 1-star question at the end. Yes, okay, so next up will be the 1-star and 2-star questions in some sequent videos, and you should see those over the next couple of nights. Thanks guys, have a good one, bye.